So here's a rational function, x squared minus x minus 6. And I know we've looked at instances where, and one of the things we talked about was the vertical asymptote and the horizontal asymptote. And we made the point that when the degree of the numerator is lower than the degree of the denominator, that and then the horizontal asymptote is the x-axis or the y equals 0 line. When they were equal, we took the ratio of the lead coefficients. Now all of a sudden, we have one where the numerator has a higher degree than the denominator. So I'm wondering now, would this have an HA and would this have a VA? And what might this look like? Any guesses before I put this on the smartboard, before I ask the smartboard to draw this line? If you had to guess what this line looked like, what would your guess be? It may not have a VA, no, I was thinking, just a guess. Interesting. So let me just see if I can turn my thing over here and get going. So the first guess we have is that there is no VA. How about an HA? Do we think there's an HA? Does anybody think there's an HA? And if there's an HA, what do you think the HA is the question. Before I draw this, no other guesses apart from Noah? All right. All I hear is silence right now. Noah is the only one. Okay, let's just see it. Isn't it just a straight line? Ava thinks it's just a straight line? Really? Why would you think that, Ava? That's an interesting observation. Why do you think it's just a straight line? Did you go and draw it, Ava? Is that what you did? Did you go over to Desmos and draw it over there? Because degree 2 divided by degree 1. Oh, I see the thinking now. I see the thinking. And I'm still curious as to why Ava thinks it's a straight line. Where did Ava get that from? I was thinking it might factor in. Ah, okay. So that may be where Ava might have gotten her idea from. Because, yes, if you think about it, the top of this function is factorable. So it means that if I factor the top, I'm going to end up with x plus 2, x minus 3. And that's all over, of course, x plus 2, which means that, yes, this cancels out with that. So really what I'm left with is simply x minus 3. So is this just a standard straight line? Well, it is not. Let me first of all draw this for you. There's your straight line, but it's, even though the smartboard draws it as a straight line, I was thinking exactly what Jerry thought. Okay. No, that's it. What it is no, we're going to look at the instances where the top is higher than the bottom and what that means in a second. But really what is happening here is that this function, which is rational, it is a rational function. All rational means, just for a definition, is that it has a numerator and a denominator. That's all rational means. Right? But although it is a rational function, it does simplify to a straight line, but with something called a hole in it. Right? And we're going to figure out where the hole is right now. The smartboard doesn't show where the hole is, but there is a hole because there is a restriction on the original function. What would you say is a restriction on this function? What can x not be equal to based on the original function? Right? Look at the original function. X cannot be equal to minus 2. That's exactly right. So it means that at minus 2, which is right here, I should have a little circle, which means that the function actually doesn't exist at that point. It's called a hole. Now, as you can see from the graph, that hole is at minus 2, minus 5. Right? Now, how could I get that without the graph? Okay, so I have the graph to show you that, in fact, the hole is at the point there that is non-existent or discontinuous. Here we go. Let me change that. It's not an asymptote at all, because an asymptote would be a line that the function is approaching. That's not what's happening here. This is called a discontinuity. And when you go to calculus, so a lot of you will be doing calculus later on. This is a discontinuity in the graph. Discontinuity. And the type of discontinuity is a hole. There are other types of discontinuity. So a vertical asymptote is also a type of discontinuity. But that doesn't mean that all discontinuities are vertical asymptotes. So I just want to make sure we understand that, because there are other kinds of discontinuities, such as a hole. And a hole is one of the types of discontinuity. And all that is happening is that the function is this straight line. So you can follow this function, straight line, straight line, straight line, straight line. I'm using my mouse to show you straight line, straight line. And all of a sudden it hits this point where the graph stops at that one exact point right there. Then it picks it up again on the other side, and then it continues as a straight line. So this is referred to as a hole, but not a vertical asymptote. This is not a vertical asymptote. I want to make sure. So this is the term that we'd use, which is a type of this, but not a vertical asymptote. Okay, I just want to make sure that's clear to everybody. Let's get the terminology right here. Now, what if I didn't have the graph here to show you that the hole was at -2, -5, right? Well, what I could do is, first of all, figure out what where the discontinuity is, which is that x equals -2, and put that -2 into the function here that's left over. So -2 minus 3, of course, is the -5. So -2 minus 3 is equal to -5, and that's where the y value is, as Noah is saying, just plugging the -2 back into what's left of the equation. After you reduce it down, what's left. You couldn't put that -2 back in this original equation. The equation would blow up. That's my term. That's not a technical math term. That's just what Mr. Kamak uses to describe when a function is undefined. It blows up. But don't use that term outside of Mr. Kamak's class, because that's not the right term. But I couldn't put -2 into this original function, because then the function doesn't work anymore. But I can put -2 into the reduced version of the function, and that would give me the -5, which is the y value at the hole. Okay? So this is not to be understood as what happens when the numerator has a higher degree than the denominator, because in other cases, something else will happen, which I'm going to get to in a minute. So this is what we call a special case. And a special case is when the function seems like it's one thing, but it's really something else. And it works out to be this regular straight line. Okay. So I am going to go on to my next page. And as you can see, I took a screenshot on this next page of a Desmos screen. If you put this same function that I just had here in Desmos, you will see that it looks like a straight line. If you put your mouse right over that spot, then the hole will open up. And I took a screenshot of that so you could see what that looks like on a graph. So if you're drawing a graph like this one, you should always put a little circle there to say that the function has what's called a hole in it. Okay? All right. Let's get to the next one. What does this one look like? Well, we're going to do the same thing again. But does this mean that the horizontal asymptote is at x equals 1? Well, it might be. But the first thing we have to do is we have to figure out if this can be factored and can this be reduced. So this is when we need the magic x, by the way. Some of you seem to have grown fond of the magic x. I'm going to use the magic x on this one for both the top and the bottom. Some of you don't need it because you have other ways of doing it, but I'm going to use the magic x. So the top of this is going to be -8, and the bottom is going to be -7. The two numbers, and I'm going through this fairly quickly because I've explained how this works before. The two numbers I'm going to need to make this work are -8 and 1. So those are the two numbers that multiply to give you the -8 and add up to give you the -7. I'm going to divide both of these numbers by 2, right? And that 2 comes from the first 2 right there. And this becomes, when I reduce it down, -4 over 1. This one can't be reduced anymore. So it means that I now have x minus 4 and 2x plus 1. Okay, so that's my numerator, which has been factored. I'm going to use the magic x again. And for the bottom, so I'm going to have 4 on top, and I'm going to have 5 on the bottom. The 2 times 2 gives me the 4. So just to make sure we understand, this 2 times this 2 gives me the 4. And the 5 comes from the middle. So the two numbers I'm looking for are 4 and 1. 4 times 1 gives me 4. 4 plus 1 gives me 5. Divide both of these numbers by 2 again. This reduces down to 2 over 1, and that's just simply 1 over 2. So it means that my two factors are now going to be Oh, I see why that happens now. I got you. So I need to hit it with that then. Okay, that happened yesterday where I used the mouse to select the color and it didn't change the color. Okay, so anyway, so x plus 2 and 2x plus 1. Okay, so again, what's happening is that part of this function gets eliminated or reduced. So here, actually, I want to use red for that. So this, and what's left is just simply x minus 4 over x plus 2. Now, I'd like us to try to remember how to sketch this even before, and then we have to find where the hole is, by the way. So there are two things we need to do here. I'd like us to see if we can sketch this without using Desmos or without using the smartboard. So this is a revision of the stuff we did yesterday. Let me start off with, where is the let's start with the VA actually. Where is the VA of this? Where's the HA of this? What about the x and y intercepts? X-intercept and the y-intercept. Let's start, because with all of those things, we should be able to sketch the function, and then we can use the technology to confirm that we get everything right. So let's start with the VA. Can somebody give me the VA? The VA, and given with the equation, which is perfect, is x equals minus 2. Okay, how about the HA now? Thank you very much, Noah, and thank you very much, AXA. And how about the HA now? Okay, a bunch of people are saying y equals 1. Well done. All right, if anybody's sure where they're getting all of this stuff from, thank you, Emily. Thank you, Jeremy. Thank you, Harish. Excuse me. Thank you, Noah. All of you are 100% right. Y equals 1. How about the x-intercept? Again, the equation tells us where that x-intercept is. It's at 4. Remember, x-intercept comes from the numerator. All right, look at the numerator. What makes that numerator become 0? That's your x-intercept. Okay, good stuff, Noah. Good stuff, Harish. How about the y-intercept? What's the y-intercept, folks? Help me out here. Minus 2. Thank you very much. So I have a pretty good idea of what I'm dealing with here. I'm going to first of all put in my asymptotes. All right, remember, asymptotes have to be dotted lines. When you get your summative assignment, please remember that. So I'm going to put in my vertical asymptote and my horizontal asymptote and put them in red. Okay, so here comes my vertical asymptote at x equals minus 2, so somewhere around here. And my horizontal asymptote, y equals 1, somewhere around here. Then I'm going to put in my x and y intercepts. So let's put it in red. So my x, or maybe blue. Let's go with blue. So my x-intercept is at 4, right, around here. And my y-intercept is at minus 2. So you know what? Once I see those two things, I know where this is heading. That means that the graph's going to look something like this on this side. Oh, I don't know where that last line came from. And something like this on this side, roughly speaking. They're about, actually, let me change that last one a little bit. They would be approximately the same distance away from the center of the two, where the two asymptotes meet on both sides. So this one up here is going to be maybe a little bit off. I'd say I have more confidence in this side over here. But here we go. Let's ask the smartboard to help us out to put that together now. See how close we came here. Oh, come on, don't. Sorry, folks. It's being a little bit. You can hardly see the lines behind there. Right, I know this isn't a big deal, but aren't the factors 2x minus 1? No. It's 2x plus 1. Just no, it is 2x plus 1. Here's how I know, right? Here's how I know that it works. And by the way, let me click off here. If I were to multiply the minus 4 in this bracket and the 1 in this bracket, I get the minus 4 on the end. If I multiply the 2 in this bracket and the 1 in this bracket, I get the plus 2 on the end. So that's one of the ways, that's one of the checks I can use for me to know that that's right. Okay? You can double check that. Okay. All right. So I'd say that my graph isn't that bad at all. I'd say without sort of sounding like I'm patting myself on the back here. I think I did a pretty good job. Okay, you can hardly see the difference between the smartboard version and Mr. Kamak's version. So pretty good job. And yeah, you know what? I'm going to slap myself on the back and say, yeah, that's actually not bad at all. Now, on a serious note, there's a hole. There is a hole in this function. And can anybody tell me where that hole is? What's the x value of where that hole is? The smartboard isn't showing it very well. Smartboard doesn't show it at all, right? Where the hole is. But there is a hole in the function, and I want to make sure I draw that in. So where would I find that hole? Where is the x value of that hole, right? Remember, go back to the original function that I'm pointing to right now. Right? What value of x would cause you to have a hole? Well, it's this thing that I eliminated, that I reduced out, the 2x plus 1. What makes that, well, it's not minus 2, no. What makes this become 0, right? Because that's what's going to cause the problem. So it's not minus 2, it is minus a half. That's correct. So take that 2x plus 1, and first of all, let me erase all of this here, because we really don't need all this stuff here. And what we're going to do is we're going to say, okay, so let's take that 2x plus 1. Oh, blue. Okay. Set it equal to 0. And we're going to end up with x is equal to minus a half, which means that this is my restriction. So x cannot be equal to minus a half. Thank you, Harish, and thank you, Ava, for that. So now we can say that when x is minus a half, which is somewhere over here, we're going to have a y value, which we need to figure out. And for us to figure that out, we're going to put that back into what's left over. And what's left over is this, x minus 4 by x plus 2. So to get the whole, go back to black, to get the whole, this is the calculation for the whole now. Right? I know the whole occurs when x is equal to minus a half. So I'm going to put that minus a half that Ava and Harish told us about, put that into this x minus 4, x plus 2 that's left over. So minus a half minus 4 over minus a half plus 2. So that's going to give me my y value of this whole. That's what I'm trying to figure out here. So I don't intend to teach you fractions, folks. Minus half minus 4.5 is minus 4.5. All right. And a half plus 2 would be positive a half, positive 1.5 rather. I'm going to turn these both into improper fractions. So that's minus 9 over 2. And then I'm dividing that by 3 over 2. And just reminding you that when I divide a fraction by a fraction, I can multiply the top by the reciprocal of the bottom. So what I mean by that, that would be minus 9 over 2 multiplied by 2 over 3. Right, so I'm taking the bottom of the fraction, which is a 3 over 2, and I'm flipping it over and I'm multiplying it. 2's will cancel. Minus 9 divided by 3 is minus 3. So here is my coordinate. Here is where the hole is. The hole is at minus a half, minus 3. Okay, and I can go back and look to see whether the graph has roughly put it in that position. And what I'm going to do, in fact, is I'm going to erase my drawing, as really nice as it is. And I'm really proud of my graph, but I'm going to take it away for a bit. And I'm going to go ahead and put in the minus a half, minus 3 as a whole right about here. Okay, that's the location of my hole. And I should always use that little circle to make it clear that there's a hole there. So if I just move forward a bit here and I look at the Desmos version of the graph, you can see the same thing here, the little circle right there, minus a half and minus 3 right there. That's the point that's undefined. That's the point that I have what I'm referring to as a hole. So let me just review this one more time with you. Top of the function was what looked like a quadratic over a quadratic. But when we analyzed it and we sort of reduced it down, factored it, turns out that it was just a linear over a linear, which we've done before. And we knew that it had certain characteristics of VA and HA, which was easy to identify, an x-intercept and a y-intercept. And by the way, if any of these features that we just figured out, you're not sure how we got them, you need to let me know so that I can go through it more slowly for you. Then we also figured out where the hole was. by saying, well, what is the thing that made this thing blow up? Again, my term, not a technical math term, and that is when x is equal to minus a half. So this is the restriction on the original function, and putting that into the reduced function gives us the minus 3, which is where we have the whole. Okay, let's get to something else. Oblique asymptotes. Things are going to change for us now. I want you, I shouldn't have this here yet. I'm going to put this out of the way for now. I'm going to let that sort of slide. I'm going to leave that on the side there, and I'll tell you where that comes from later on. If I were to draw this, no, the top of this cannot be factored. All right, let's just accept that. This cannot be factored. But it turns out it still has an asymptote, and a kind of asymptote that we haven't seen before, which is called an oblique asymptote. And maybe I should just go ahead and draw it, show you what it looks like. And let's put in the stuff we know first. Let's put in all the stuff we know. Let's talk about the VA. We're not going to talk about the HA yet because we don't know what that is. In fact, it's not even an HA, it's called an OA for oblique asymptote. But we certainly know the Y and X intercepts. So let's start off with the Y-intercept. Do we know what the Y-intercept is? Well, remember how to get the Y-intercept, folks? What's the Y-intercept of this function? Anybody? Help me out here. 5 over 2. Thank you. Or minus 5 over 2 is probably what you meant to say, right, Ava? So we know those things at least. X-intercept is going to be difficult because this can't be factored. We're going to have to go ahead and use a quadratic function to be able to figure out where those x-intercepts are. So we'll leave that out for now. Certainly possible. But we don't have a VA though, don't we? Can you give me an equation? Let me stress that. Give me an equation for a VA. An equation. Okay, a little bit too quick on the draw there, AXA. All right, so Emily says x equals minus 2, and I absolutely agree. So I can put that in right now. I can put in that vertical asymptote. There is another asymptote which we're going to talk about. By the way, is everybody clear on what Emily is saying? Does that make sense to everybody that there is a vertical asymptote at that point? Isaac, how about you? Does that vertical asymptote make sense there? Isaac, you there with us? Okay. All right. So there are x-intercepts. Let me just be clear on that. There are x-intercepts, but so far we don't really know. We can figure it out because we can use a quadratic function to figure it out. But let's now see what this graph looks like. This is interesting because here's a case where I can't factor it and reduce it down. X plus 2 is not a factor of the top. And it has this unusual case where we haven't really talked about yet, where the numerator has a higher degree than the denominator. So Mr. Kamak is talking about oblique asymptotes. What does that mean? Well, let's draw this first. Let's see what this function looks like. Whoa, who saw that coming? Well, part of it we certainly know, and that is that there is a vertical asymptote. Let's go ahead and put that in. That part nobody was surprised at because we've seen these vertical asymptotes before. So that one shouldn't surprise anybody. So x equals minus 2, somewhere about there. Makes perfect sense. Makes perfect sense. But now there seems to be another asymptote. And I'm saying that asymptote seems to be this line right here. Let's put that in as well. But why x minus 4? That's another asymptote, but it's not a horizontal line anymore. It's a line like a y equals mx plus b kind of line, and it's x minus 4. So I wonder where that came from. I wonder if there's a way that I could figure out that asymptote from the original function. That's kind of what I'm a little puzzled by right now. How did we come up with that x minus 4? Because clearly, I mean, if you follow this thing, you can see that it does follow this vertical asymptote, which we were completely ready for. But now we're seeing this other asymptote, which the function is following. Look at the function moving towards this asymptote here, moving towards this asymptote over here. If I can make this into a dotted line, is that possible at all? Let me just see. Properties. I guess not. Or maybe, hmm. Yeah, I just wanted to see if maybe I could make this into a dotted line rather than a, no, maybe not. Maybe not. No. Okay. So maybe I can't make it. I like when I'm putting in division, no, I was thinking. Huh. Interesting. So you're thinking division. Tell me what you expand on that a little bit for me, please, because you are on the right track. What kind of division are you talking about? And how does that division lead us to this x minus 4? So Noah, just so you know, you just put division in the chat, is saying division seems to be the missing link here, the thing that is going to lead us to this x minus 4 asymptote. It is, in fact, an asymptote. And you can tell, just look at how the graph is moving. If I move this graph, let me just do this here. If I move this graph further this way, it's still trying to hit that line, but never hitting it. Same thing on the other side, right? It's still moving towards it on the other side, never hitting it. And the other asymptotes that we talked about are absolutely still there. Oh, actually, you know what? This line doesn't move with the graph, so that's why it's not. It's this asymptote is one I put on the graph, so it's not moving with the graph. So at any rate, if I go up or down, it's still moving towards that x equals 2. Let's put the thing back at x equals 2, x equals minus 2 rather. All right. So, Noah, what do you mean by division? Because you're on the right track, but how do we use division to get this oblique asymptote? Because that's what we're dealing with here. It's a line, an oblique line, that connects to the graph somehow as an asymptote. Can you be more specific, Noah? Can you give us a little bit more so that we can see how we can go from one to the other? Okay. Mm-hmm. Oh, okay. Okay, let's try that. Let's see what happens. Say that you might have something there. So here's our equation. And this equation, not equation, function, this function. And this function is made up of a numerator and a denominator. Let's move this out of the way here. Right? And right now, this denominator of x plus 2 means that I can write this in what we call quotient form. Let me remind you about something. When I have a fraction, like maybe, let's just make up a number here, 8, oh, sorry. If I have a fraction, such as 8 over 5, right, which is kind of like what this is, that's a fraction, I can write that as 1 and 3 over 5. It's still the same fraction. These two things are identical to each other. They equal each other. So there's a whole number part, which remember when we were talking about this, we call the quotient. Right? And we put this thing we call the remainder. I just use REM for remainder. And this other thing down here we call the divisor, div. Okay? Try to remember that from before. So when I took this dividend of 8 divided by this divisor of 5, I ended up with a quotient and a remainder over the divisor. So what that suggests is this. I can rewrite this thing in quotient form. And we're going to try to do that right now. Let me clone this, right? And rewrite this thing in quotient form. Quotient form means with a quotient and a remainder over a divisor. 8 over 5 is the same thing as 1 and 3/5. They're the same. There's a different way of expressing it. So I'm going to express this thing here in quotient form. So here we go. For us to do that, we have to do a division. We're going to use synthetic division that some of you like, some of you not so crazy about it. But I'm going to do synthetic division. So here's my little chart. And I'm going to put the plus 2 on the side, and then the 1, the minus 2, and the minus 5 on the end. Okay? So bring the 1 down. We've done this before. 2 times 1 is 2. Put that 2 here. Minus 2 is minus 4. 2 times minus 4 is minus 8. Minus 5 minus 8 is like saying minus 5 plus 8, which is 3. So here is another way of writing this function. So this function here, I'm going to rewrite it right now. I'm going to say that this is exactly equal to This part here is my quotient, x minus 4. So that's like this 1 that we had up here, plus 3 over the divisor of x plus 2. So what I'm saying to you is that this thing that I'm going to circle right now is the equivalent of this thing here that I've just circled over there. They are the same function. If I were to go to Desmos right now, and I were to draw the first function, and I were to draw the second function, you couldn't tell I had two different functions because they are the same. The only difference is that this one is in what we call quotient form, which means it separates the quotient from the remainder over the divisor. This is quotient form. Now, one of the things that I taught you yesterday, or maybe before yesterday, yeah, probably before yesterday, is that if we're talking end behavior, as x gets bigger and bigger and bigger, in fact, let me pause this for a bit. We talk about the end behavior of this function, and as x tends to minus infinity or x tends to infinity, y tended to go towards the asymptote. It tended to move towards the asymptote. So as you got bigger and bigger and bigger, it just simply moved towards where the asymptote was. Hope everybody remembers that from when we did this stuff 2 days ago, I think it was, or maybe yesterday, I don't remember now. Right? So the asymptote is what the function seems to move towards as you get bigger and bigger. In fact, when we were doing the ones where the asymptote was the x-axis, which is the y equals 0 line, the function moved towards 0. So the asymptote seems to determine what happens to the function as you get bigger and bigger and bigger. So let's go back and look at what we're looking at today. Right? So I'm going to go back to the page that we were on. Right? The oblique asymptote. So what do you expect to happen as you move further and further to the right? Well, what's happening is that as you move further and further to the right, the function is moving closer and closer to the asymptote. And the reason for that is what we can look at here and determine. What happens as the denominator of this function? Look at the denominator here. The denominator is 3 over x plus 2. What happens as this x gets bigger and bigger and bigger? What happens to this part of the function right here? Right? What happens to the part that is the remainder divided by the quotient? As x gets bigger, let me see if the class can help me out with that. What happens to this rational part of the function? Let me circle it in a different color, right? What's going to happen to this part of the function right here? As x gets bigger and bigger and bigger. The bigger x is, what happens to that circle? What happens to the size of that, the part that is in the circle? Does it get bigger or smaller? What happens to that? Help me out, folks. Let's say that x was, it gets, yeah, in fact, it is actually tending towards 0. Thank you, Noah. So what's happening is that this part of the function is disappearing. So what's left is just this. The function is going to behave more and more like just simply x minus 4. So the quotient is what is going to be your asymptote because the function is going to behave as if this part doesn't even exist anymore. It doesn't go away completely, but it's less and less of a factor. And therefore, that's why the function behaves much more like x minus 4 as you go towards infinity. So the bigger you get, or the smaller you get, which is minus infinity, that part just seems to behave just like the x minus 4 line. And that's why when you do that division that Noah suggested, when you do the division, you're just left with the x minus 4, and that's why so the quotient becomes the asymptote, right? And that's how you get that oblique asymptote. Now, can you have other kinds of asymptote that are not oblique? You absolutely can. How would you graph this? We would have to find the roots, right? Well, yes. The numerator is where you're going to get the x-intercepts from. And if it's not easy, like in this case, then you'd have to use the quadratic function to do that. Okay, Noah? So, but once you have the x-intercepts, then you can put, and we can at least have, you can use, your calculator to do the quadratic function. You would have those x-intercepts and you could figure out where the y-intercept is as well, because we figured out minus 502 right down here. And you could draw this. It is possible for you to sketch almost any graph if you know the main features. Okay, so that's what this is. That's what is going on here. You have something called an oblique asymptote, and you get that from dividing the numerator by the denominator and looking for the quotient, because the quotient would be your asymptote. Now, I said oblique because it's not a horizontal line. It is actually, it's still a line, but it is a line with a slope of some kind. So it could be negative, could be a negative or a positive slope. But if it was horizontal, it would be a horizontal asymptote. Now, I probably should show you a case of where, what if the numerator was a degree 3 and the denominator was a degree 1? What kind of asymptote would you expect in a case like that? If you had to guess, what kind of asymptote would you get if the numerator was a degree 3, cubic function in other words, and the denominator was a degree 1? Just tell me what you think the asymptote might look like. I could show it to you on Desmos in a minute. That might not be a bad idea. But what do you think, folks? What kind of asymptote would you get if the top was a degree 3, a cubic function, and the bottom was a degree 1? Anybody? Any suggestions on what that might look like? Something weird. I was hoping for something different apart from something weird. I tell you what we'll do. Why don't we try that right now? I'm going to open up, before I get to my next page, I'm going to add a page in, and I'm going to use my math type to put in a cubic function. So let's try this. Fraction first. Here's my fraction. I'm going to put the x on top to the power of, let's say, 3. And then maybe minus x squared. And then maybe plus 2x. I'm making this up completely on the fly here, folks. This is not rehearsed in any way. Minus 2. Okay, I have no idea whether this is going to work or not. Then the bottom will make this a x plus 3. X plus 3. No, plus. Okay. All right, so let me delete this. And let's see if we can get the smartboard to draw this and then figure out where the asymptote is. All right, can you draw this, Mr. Smartboard? Whoa! Whoa! Well, one thing we knew was that there was going to be a vertical asymptote, right? Vertical asymptote was going to be at x equals minus 3. Can we all agree on that? X equals minus 3. All right. Okay. What about, ooh, what's wrong with my graph? You don't like my graph? Looks so weird. Does anybody have an idea what kind of asymptote the other asymptote is, though? I'm going to tell you that it is not going to be linear. Can you guess what kind of degree that asymptote is? Anybody? Nobody? It's a degree 2. Thank you, Jeremy. And thank you, Noah. And that's because if I divide this x plus 3 into that, I'm going to get a quotient, which is a quadratic function. Okay, since I made this up, let's try this out and see how this works. And then we're going to put that quadratic function on here so you can see that it does have a vertical asymptote at x equals minus 3. We can see that. That's quite evident. But it also has some kind of a quadratic function. So let's try that. Let me grab my stylus here, and I'm going to do a division. This wasn't what the lesson plan called for, but we're going to try it out anyway. So here we go. I'm going to put a plus 3 on the side. And so there's a 1, a minus 1, a 2, and a minus 2. Okay, so I think I have everything there. A cubic, a quadratic, 1, and okay, good. Bring down the 1. So that would be 3. And then 1, so that was a minus 4. And then minus 12. So that would be 14. And 3 times 14, 3, 12, 0 and 3, is that 48? What is that? I'm doing this in my head, folks. Help me out. Is that 48? 42, of course. Yeah, that makes more sense. That makes a lot more sense. 42 makes a lot more sense. Sorry. 3, 4 is 12. Yeah. All right, let me take that away. 42. This would be minus 44. No, the important part is not so much that part, not the remainder. The important part is the quadratic. So if I did everything right, which I think I did, we're getting a quadratic as our quotient of x squared minus 4x plus 14. So what I'm about to do now is I'm going to put that graph on here, the graph of this function, and see if it looks like it is in fact the asymptote for this function. So we have one asymptote here at x equals minus 2, which is clear, right? That comes from the denominator. I'm going to put this other function on there now. So let me go back to my math tools. And we're putting in, I don't need a fraction this time. Putting in, oh, sorry, x squared minus 4x plus 14. Okay, so I'm going to get the smartboard to draw. Again, the remainder doesn't matter. Well, it matters, but for the asymptote purposes, that's not what we're trying to figure out here. So I'm going to go ahead and see if it will draw that line on it for us. Look at that. There you go. And that was completely random. But it is clear, or hopefully it is clear to you, that this function is following this asymptote. It is following the vertical asymptote as well. So there's a vertical asymptote right here. But it's also following this. It's not an oblique line. It's a quadratic line that the function is moving towards on both sides. Okay, as weird as you all said it was, you didn't like my graph, you didn't like my function. That's okay. I'm not taking any offense. I'm okay. I'm good with it. I'm cool with it. But you can clearly see that it does have two kinds of asymptotes. One is a quadratic function, and the other one is a vertical asymptote at x equals minus 3. Okay? Was that demonstration clear enough? So if I ask you to find an asymptote for any rational function, you should now be able to find it, whether it's a vertical asymptote, a horizontal asymptote, an oblique asymptote, or even a quadratic asymptote. This is not an oblique. No, oblique is usually refer to oblique asymptotes for straight lines, Jeremiah. So you don't have an oblique asymptote if the numerator was 1 degree higher than the denominator, in which case it would be linear. So this one would be a quadratic asymptote. Okay? All right. So again, that was a little bit off of the course I had planned, but I thought it is a useful thing for us to share with you. Okay, so let's go back now. We've got that done. We've got this done. Okay, so your turn. Can I get you all now to hall pass? Omar is asking for. Okay, Omar, it's 11:57. I expect you back within 5 minutes. Can I ask you to get me the equation of the oblique asymptote for these three functions? No, everybody, please. Work out those oblique asymptotes for those three functions. And all I'm looking for is the equation of those oblique asymptotes. Go, everybody. So Neil is saying x minus 2 for the first. Let me write that down. X minus 2 for the first one. Or y equals x minus 2, just to be more specific. So y equals x minus 2. We're going to come back to that. And let's see. No, so that was Neil. I'm not asking anybody if they agree with that yet. We'll just leave that out for now. Let me get the equation of the asymptote for the next one from Riddy. Riddy, I think I'd ask for a hall pass. Let's see if. Okay, is Riddy back with us now? Should be back with us by now. Riddy, are you there? Okay, not done yet. All right, we're going to come back to you. Going to come back to you shortly. So that was Riddy. And I need the one for the third equation. I need that from AXA. AXA, do you have an equation for us for the last one? That's the oblique asymptote I'm looking for. AXA, do you have that there? X minus 1, you say? Y equals x minus 1. I'm going to write that in. All right. So I'm going to come back to Riddy now and give you a chance to get that done. I do need that from you though, Riddy. If you're not sure how to do it, then please let me know. I can give you some help, but I need it from you. Rachel, do we not include the remainder? No, not. That's the point I'm making, Rachel. That is not part of your. What happens is that the remainder is disappearing over time as x gets bigger and bigger, and the function really is just behaving more and more like it is just the quotient. Okay? Right. Okay. So you have, is it x minus 1? I'm going to put that down. We'll see. Okay, so what I'm about to do now is ask the smartboard to draw each of these functions and see whether x minus 2 makes sense. Okay, so here we go. Generating a graph. Oh, sorry. Oh, that doesn't look like the graph at all. What is that? That does not look anything like our graph at all. X squared plus 3x minus 7 over x minus 5. Oh, that's interesting. How come this is a straight line? What's going on here? First person only x minus 2. So what's going on? Can anybody tell me what's happening here? The top is factorable. Interesting. Because it is an x plus 5, it cancels out. So really what we have here is not a oblique asymptote at all. Right? What we have is a straight line, which means that this has a hole in it when x is equal to minus 5, not an oblique asymptote. Does that make sense to everybody? Right? Just want to make sure we're good on that. So I see what you did. You did your division and all of that, but the fact is that x plus 5 is actually a factor of the top, so it's actually just a straight line. Does that make sense? So I want to make sure everybody's okay with that. Okay. Let's try the second one. So I'm going to delete this now. So this is actually not an oblique asymptote at all. What this is just the other factor that you get from this function. Let's try the second one. I'm going to delete this. Actually, I'm just going to cancel this out here. Let me disconnect this. And I'm going to try drawing this one and see what happens here. Oh, this one does look like it might have an oblique asymptote. And is that oblique asymptote x minus 1? So what I'm going to do is I'm going to get the smartboard to put in the graph of x minus 1 and see if that actually works. So let's put in the x minus 1 and then ask the graph, the smartboard, to draw that line in. It looks like it works to me. Does it look like it works to you? What do you say, folks? I think that came from Riddy. Does that look like the right asymptote to you? Riddy, what do you say? Do you think you got it right? Okay, Emily says yes. How about Riddy? Riddy, are you proud of your work? Does the x minus 1 look like it? Okay, all right, let's try the third one. All right, so I'm going to delete this now. So I'm going to disconnect that. And I'm going to disconnect this. We're going to go down to this one. The person who gave me this one, and I forget who it was, sorry. I think it was AXA, I think, who gave us this one. Said this one was x minus 1 as well. Okay, so let's see. Let's see what this looks like. Okay, so this one looks like it could be the same asymptote as this one. So let's find out. Okay, so hang on a second here. Why is this not allowing me to graph this here? All right, tell you what I'm going to do. I'm going to disconnect that. I'm going to delete this completely. And I'm going to start from scratch. So here we go. Okay, so there's our graph. Oh, that's weird. Why is that not working now? Come on. Okay, let's try putting another math thing in. Let's delete this one. I don't know why this one isn't working for some reason. Let's try putting another math equation in. So x minus 1. Oops, sorry. Does that look like, was it AXA who gave me this other equation, by the way? X minus 1, I forget who it was. Was it AXA? I could go up to the chat and see. I think it was AXA. Who was it? Who was it that gave me the second? The third was AXA. Okay. Do you think that looks like it might be the right asymptote again for this one, AXA? Does it look like you hit it out to the park on this one? I would say it looks like it does. Okay, let's move on. We have, I think, one more question I want to get to. And then we're going to try a poll. I said if we had a chance at the end, we would try a poll, which we will if we get through this question. So thank you very much for all that input, by the way. Now, this question is sort of trying to make a connection again between the math that you're learning in class and the real world. So some of you probably know about a phenomenon which divers have to be aware of, which has to do with, when you go diving, and when you go down to certain depths, you have to gradually come out of the water. You can't just come up very quickly because you can actually get bubbles forming inside of your veins if you do that, and it's called the bends. You can research that and you can learn. You can talk to your science teachers about that. But anyway, let's just read this through. The maximum time in minutes a scuba diver can rise without stopping for decompression on the way up to the surface is defined by the equation, and you give us an equation here. They also say that D has to be greater than 10, not greater than or equal to, but greater than 10. And you can see that if D was in fact less than 10, that this thing would be negative. All right? So that's why the domain of this function is that D has to be greater than 10. Okay? D is the depth of the dive in meters. For the maximum time to be less than 30, how deep can the diver dive is the question. Okay? How deep can the diver dive? So the thing we have to figure out is how can we set this up to solve it? So this tells us what the time is, and we want the time to be less than 30. Can you suggest a way that I could mathematically calculate that? Right? This is the function that tells us what the time is, given what the depth is, right? D is the depth. And we want to solve this for the depth, given the time of 30 minutes. So set everything to be less than 30. Okay, so let's do that. So here's the function, 525 over D minus 10. So I'm going to go ahead and write that in. So 525 divided by D minus 10 is, less than, is less than 30, right? That's what we want. We want this thing here, this maximum time to be less than, this gives us the time based on the depth. So how do we solve this? What's the next step in solving this, folks? So Karis agrees with Noah, by the way. I just saw that. Okay, go ahead. Noah says bring the 30 over. Jeremy is raising his hand. Put the 30 minus 30 over 1 is what he thinks. Okay, let me hear from Jeremy. Jeremy, what do you think? What are you thinking? Mm-hmm. 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 Okay. Yeah, I hear you. I hear you, Jeremy. And I also heard what Noah said, and I heard what all of you said. Guess what? I'm about to break that rule. The rule I taught you just yesterday, like 24 hours ago, I'm going to break that rule right now. I'm going to cross multiply. All right. Can somebody tell me why I'm being so obnoxious and thinking I can just break the rule? What is it that allows me to break the rule this time? Harish is saying it must be positive. Why do you think it has to be positive? Tell me, Harish, why do you think that it has to be positive? Why does that denominator have to be positive? Was there something about the question? Because the question said that D has to be less than 10. That's exactly right. Sorry, that D, if you go back to the original function, which I'm trying to get back to right now, not less than, but greater than 10, right? And that means that this thing here, this D, that we're getting cannot be any number like 9 or 8 or 7 or 6 or any of those other numbers, which would cause the problem that we talked about yesterday. So in a case where the domain that you've defined does eliminate the possibility that cross multiplication could cause that problem, then it's okay to cross multiply. So yes, I know we're about to break the very rule that we set yesterday, but that's exactly what we're going to do. Right? Didn't take time, but D isn't D isn't time, but same principle. Yes, 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 yes. So I'm going to go ahead and cross multiply. I'm going to say that 525 is less than 30 times D minus 10. Completely ignoring the rule about not cross multiplying for a inequality. We already said that cross multiplying is great for an equation, but we also said that for an inequality, it's not a good strategy, but it can be done if we have set up some condition which makes the thing that we're cross multiplying by always positive. So let's continue solving this now. So 525 is less than 30D, sorry folks, 30D minus 300. And then I'm actually going to switch this around, right? I don't like having the variable on the right hand side. So I'm going to put the 30D on the left minus the 300. And then I'm going to put the 525 on the other side. But I think we understand that if we switch around the problem like that, put the left onto the right and the right onto the left, that means that we have to change the direction of the inequality. Right? We have to change it because this inequality was pointing to the left before. Now it has to point to the right because we turn everything over. And in a sense, it's like multiplying the two sides by -1. It kind of is that, right? Which is what caused us to have this. Okay, so now we can say that 30D, I don't know why I keep saying 3D. I guess 3D kind of just sticks in my mind. 30D is greater than 500 plus 300. So 30D is greater than 320, sorry, something's wrong. 500, where's 500 coming from? 525, sorry. Somebody probably had that error in the channel. No, maybe not. 525. So 525 plus 300, so that's 825. So therefore, D must be greater than whatever 825 divided by 30 is. I need some help with that, please. Can we get what 825 divided by 30? 27.5, thank you very much. So D must be greater than 27.5, and that, of course, is a distance, which would be, I guess, meters. Let me just double check, guys. That is what it is. D is the depth of the dive in meters, yes. So what's the maximum time for the maximum time to be less than how deep can the diver dive? So he can dive, I put a statement here. He or she can dive dive more than 27.5 meters. Okay, and that's really the essence of that question. And I believe, oh, I had this one question that I thought would be useful for us to try to solve before we finish up today. I believe that's the last thing I had on the agenda. What is this here? Oh, there's two. Okay, all right, we'll do these two and then we'll stop. So I think for practice, thank you very much, by the way, Joel and Noah. For practice, let's tackle a question like this. Right? What if this came up on a homework or a quiz, or there's no homework tonight. I did say that if you had a quiz, I'll give you a break on the homework. Let's say this came up for an assessment of some kind. How would we solve this? Now, it is an inequality. Let's be clear. It says inequality. And there is no domain that says that x has to be positive or negative or anything like that. So that the x could be anything, right? So we're going to tackle this the way we tackled them yesterday, which means that we have to bring that 3 over 4. We cannot cross multiply. We cannot. That's not the strategy we're going to use. We're going to bring that 3 over 4 over onto the left side, right? So we have, just a minute to just orient myself properly here. We're going to say that 5, let me go black on this, 5 over 6x plus 2 over 3x minus 3 over 4 is greater than 0. Okay, what would you suggest we do next? What would be a good idea for us to do next, folks? Right? What do you think I would suggest? Find a common denominator. Thank you, Noah. And what would be a good common denominator under these circumstances? Right? Give me a good common denominator. Just 12? Not just 12. 12x. Okay, good. 12x makes sense. And this is all greater than 0 still. That doesn't change. Then I'm going to say, okay, what do I multiply 6x by to get 12x? The answer is obviously 2. So that's 2 times 5. Plus, what do I multiply 3x by to get 12x? The answer is obviously 4. So that's 4 times 2. And what do I multiply 4 by to get 12x? The answer is obviously 3x. So that's minus 3 times 3x. Let me give myself some more room here. Is greater than 0. Okay, let me just double check that I didn't make any mistakes. Usually if I do, one of you normally is kind enough to point that out to me. That would be 2 times 5, which is 10. That's 4 times 2, which is 8. 4 into that would be 3x. So minus 3 times 3x, that looks good. So this would be 10 plus 8 minus 9x all over 12x is greater than 0. Okay, so that's 18 minus 9x all over 12x is greater than 0. So, what do you recommend we do now? All right, I mean, we've done some stuff that's close to this, but not quite like this. So, what would be a good strategy now, you think? Right? Help me out here, folks. What might be a good idea for us to try doing at this point? 18 minus, because we still haven't actually come up with an answer yet. Simplify. Tell me what you mean by simplify. In what way? Harish, give me an idea of how we could simplify. And I agree, I wouldn't use the word, I wouldn't have used the word simple, but I think I understand what you mean. So you could factor the top. Good, that's a good idea. So we'll do that. The common factor there, I assume everybody understands, is 9. So that would be 2 minus x over 12. X, sorry, is greater than 0. Okay. And we know we can probably reduce that 9 and that 12 a little bit. All right, so maybe cancel that down for smaller numbers. So 3 into 9 gives me 3. 3 into 12 gives me 4. So here's what we really have. And I don't think we can reduce this down anymore. We have now 3 times 2 minus x over 4x is greater than 0. So we still don't have an answer yet, okay, with all of that. What do you recommend we do now? We factor the top. We have reduced it down. The 9 over 12 gives me 3 over 4. So we have 3 times 2 minus x over x is greater than 0. Right? Did we do anything sort of yesterday that might help us out at this point? One option is to draw this, by the way. I should mention that. One option is to try to draw it and then see if drawing it as a rational function would help us out. But there's another thing that I taught you yesterday that might come in handy right now. Nobody have an idea here? Can I multiply both sides of this by something? What do you think, folks? Multiply by 4x? Multiplying by, you mean on both sides, no, is what you're thinking? Okay, so, no, that was Carrie, sorry, saying multiply first. And Noah says multiply by 2x squared or by 4x squared. Yeah, okay, Carrie, okay. So how about if I did this then? I could multiply by 4x squared, or how about if I just multiplied the two sides by just x squared? That 4 on the bottom is really not going to really change things very much. So x squared on both sides. Let's see what that does if I just multiply by x squared. The 4, I don't really care about the 4 too much. That 4 is not going to really get in the way too much. All right. I mean, we could, but it's really neither here nor there. If you want to multiply by the 4 x squared, then by all means you could do that. If you think that's going to help, but that's not really the real issue here. The issue is that if I multiply by that x squared, I'm going to end up with on top 3x 2 minus x. It's over 4 still, because this x here will cancel out one of these x's here, leaving me just simply with 1x. And on the other side of this, I still have 0. Now, really, you could think of this as being just this. This 3x over, you could think of it as just being this, 3 over 4x. It doesn't really matter seriously. 2 minus x, right? That 4 is not really getting in the way. I can put that 4 anywhere as a numerator, right? Is greater than 0. No, it is at this point that we try to draw this. Where are my 2 zeros? Because there are 2 zeros of this right away. Where are my 2 zeros? Help me out, folks. Come on, we're running out of time here. I'm not going to be able to do the poll today. 0 is 1. Where's the other one? And 2. Okay, so let's mark those off. So 0 and positive 2. How does this function look? Does it open up? Does it open down? Thank you, Emily. Thank you, Harish. Does it open up? Does it open down? How does this function look to you? Up or down? Look at the graph. Look at the equation, rather. Does it open up or down? If I were to multiply this out, it opens up. Noah thinks. Karis, everybody thinks it opens up. Everybody in agreement with that? No. Oh, hold on. Change of heart. All right. Looks like we had a change of direction there. There is a negative. Ah, okay. So it opens down then. If you multiply this out, you're going to get a minus x squared, a minus 8. So now can we answer the question is what we're about. Can we now answer the question as to where this function is greater than 0? Right? What is the answer to the question now that we have a picture to help us to draw it? Right, from 0 to 2. One more quick one, and then we'll stop for today. One more quick one. How about this one? All right? How about this one? Where is 6 plus 30 over x minus 1 less than 7? First step is to do what? Go ahead, please, Noah. Is that Noah's hand up? Yes, Noah. Sure. Yep. Tell me how. Okay, all right. Let's go see if we can. And I like that, Noah. Noah was, sort of rethinking it, and I really, really like that. And so anyway, let's move on to this one. What's the next step? In the 4 minutes that we have, you have no homework tonight, folks. So I'm gonna push this right to the limit. Okay, you're getting a day off from homework. By the way, please make sure you finish that quiz, everybody. All right. So if you had trouble uploading and all that stuff, the board will still be there. If you need the link for me to send it to you again, I can put it into the calendar for you to make sure you get this done. So if you didn't finish that, then yes, you do have homework. Bring the 7 over. Okay, good. So it would be actually minus 1 plus 30, 6 minus 7, that is, over x minus 1 is less than 0. Okay. What do you propose we do next? Let's see if we can finish this up in the 2 minutes that we have left. What do we do next? Rock the 7 over. No, is right. What's next? Come on, folks. Help me out quickly. What's next? What do we do next? Trying to solve for when it's less than 7. Common denominator. There's only Noah in the class today. Where is everybody else? I know Harish and not just Harish. I have to give some credit to other people as well. I mean, Axa does jump in, and so does Karis and Emily. Yes, absolutely. But there are a lot of people I don't hear from though. But Noah and Harish, especially Jeremy, and yeah, there's some people who are always stepping up. Anyway, common denominator. Common denominator is the x minus 1. Okay, put this over 1. And we're going to ask, what do you multiply this by to get that? It would be, so it's minus 1 times the x minus 1. And then we're going to have the plus 30. Hopefully that makes sense to everybody. Okay, hopefully. So I don't have to spend a lot of time on that. Less than 0.